Everyone. So let's get started with the next session. So I'm very pleased to introduce our next speaker, which is Marcel Hinsche from the Free University of Berlin, who will tell us about the learnability of the output of local quantum circuits. Please take it away.
Hello everyone. Thank you for the kind introduction. Before starting, I just should quickly check. Yeah, okay. Thank you. Before starting, I'd like to. Oh, there's a question already.
So two things. One of which is, could you maybe get a microphone because your voice is a bit quiet?
Okay, I can try to speak up.
But the other one is, do you mind questions being asked during the talk, or do you want to start until the end?
I think I'd like you to wait because I've scheduled it pretty tightly. Yeah. So should I use a microphone or is that volume? Okay. Okay. That's the one. Hello. Check.
The wearable microphone works.
Well,
So
wearable.
trying to switch on.
If you can turn it on.
I could go right.
Okay. So, how to
Just click this. I guess.
check. Okay. Can you still hear me? Can you hear me? Cool. Okay, so let's start again. Thank you for the kind introduction. Also, I'd like to thank the organizers for putting the conference together and giving me the opportunity to speak here to you about our work on the learnability of the output distributions of local quantum circuits. My name is Marcel, and this work is actually what I'm going to tell you is only half on the archive yet, and there's another publication hopefully coming out very soon. So don't be confused if you don't find everything that I tell you here, also there already. And now I'd like to also take the opportunity to just show you quickly who I conceived this work with. So these are my co-authors, and in particular, I'd like to point out that Marius up here somewhere is also in the crowd and is attending the conference, and certainly as happy as I am to chat about this with you. So let's get started. This is a quantum circuit, U, and as we all know, when we measure the circuit in the computational basis, say the outcome of the measurement is not necessarily deterministic, but in general probabilistic. They sampled according to some probability distribution PU, which is characterized by the circuit. And well, via the Born rule, the outcome probabilities are given by this overlap that we see here. And throughout the talk, I will refer to this distribution as the output distribution of the quantum circuit U. This is just setting up some terminology here. And in particular, I will be giving an emphasis in this talk on circuits that have some geometrically locality constraints. So whenever I say local, you should rather think something like nearest neighbor. It's just language that I've become used to way too much. And quantum circuit output distributions have been studied in recent years very intently from mostly the side of classical simulation, where the question is, when you're given a description of the circuit U, then how hard is it to sample from this output distribution? And this question is sort of at the heart of the quantum advantage proposals by Google and other Chinese groups. But this is not the perspective that I'd like to take in this talk. Rather, I intend to study, or we have studied these objects, output distributions of quantum circuits from a different point of view, namely the view of learning from data, so machine learning inspired view. And roughly, this talk is going to revolve around the scenario that I've put up here in the slide, where there's a learning algorithm, and this learning algorithm is given samples from some output distribution, PU, and it doesn't have knowledge about what U is. It only sees the samples, and it's supposed to, with knowledge of the samples, construct a model for this underlying distribution PU. That's the basic setting. And that's very much inspired by now the clicker has stopped working. Oh, now it's working again. Okay, that's very much inspired by a very common theme in machine learning, more specifically in unsupervised machine learning, where we observe some data, say in the real world, like facial images here, and we make the implicit assumption that this data was generated by some underlying probability distribution that we don't know, but which we would like to model. And so we try to come up with a learning algorithm that spits out such a model. And the idea is that we not only want to fit the input data well, but we sort of also want to generalize away so that we model the whole underlying distribution. And so far, I've been a bit loose when it comes to what I mean by a model. And when I say model, I actually want to distinguish between two types of models that one could think of, namely the density models, where the task is really to model the probability density function of the underlying distribution. So basically be able to predict the probabilities of outcomes. And in this example here with this 2D data, such a model might, for instance, be fitting a mixture of Gaussians to this data, and then you could really model the whole probability density function of the data. On the other hand, in generative modeling, the task is a little bit more subtle. Here, you want to be able, or you want to output an algorithm that is actually able to produce new examples that look like the ones that you've seen before. So for instance, you might want to use, if you have a lot of co-authors, you might want to produce new examples of them. Yeah, and so in classical machine learning, there are a lot of models that have been proposed for this sort of generative task. I've put up some here on the slide, but like a prototypical approach would be to use a neural network in modern machine learning, and to just like train the parameters so that you can do this task. And now to introduce quantum into the picture, recently a new quantum machine learning proposal was to instead use a quantum circuit for this task. I mean, it can also generate data, as I explained in the beginning. And now the idea is sort of that in this hybrid classical quantum variational training procedure, you might want to have trainable gates in the circuit here, and sort of variationally try to fit the data better and better. And just if you think about this for a moment, then it's clear that all probability distributions that you could try ever to model in this way are precisely the output distributions of local quantum circuits. And this model in the quantum machine learning community is referred to as a Born machine. Okay, so this is the prime motivation sort of for our work, at least from the practical perspective, to answer the question of what is the potential of quantum circuits for generative modeling. And some preliminary observations are that this model class is actually quite expressive when compared to other known models from the classical literature, like graphical models. And of course, in order, like, once you use circuits that are not classically simulatable, you will need a quantum computer to even run the model to at least efficiently. And this has sort of sparked the idea that there could be some sort of quantum advantage here that we might be able to discover. On the other hand, conventional machine learning wisdom is that just making your model more complex and complex is usually not necessarily a good idea. You might run into issues like overfitting or trainability issues. So just relying on more complex models might not be the way to go. Okay, so now that I've set up this nice practical perspective, I'd like to give our take on the story. We're mostly, like my co-authors and I, were very theoretically minded mostly. And so in our work, we rely on a formalization of what it means to learn from data. That is very well established in computational learning theory as the PAC model of learning, where PAC means probably approximately correct. And in this formalized setting, we can make rigorous statements about how computationally difficult it is to learn from data, also in the asymptotic limit, of course, like a very computer sciencey perspective. And even though we work in this very formalized setting, we still think that the results that I'm going to show you throughout the talk have some very concrete implications, especially when it comes to the question of ever proving a quantum advantage that that you would want to obtain via such a quantum generative model. Okay, so let me present our take on the whole issue. So that involves just quickly setting out the distribution learning framework that we are working in a bit more closely. So again, this is sort of everything that you see right now. I've sort of shown you before. There's a learning algorithm that is supposed to learn from example data, x1 to xk, where each of these x's is drawn independently from some unknown distribution q. And that's the input to the learning algorithm. You can think of it as a training set, and it's supposed to just output a model for the distribution q. Now, in the PAC model, the crucial ingredient that lets us argue about what's doable efficiently and what's not is the concept class. So rather than just modeling any distribution, the learning algorithm is actually promised that the unknown distribution that it's seeing the data from belongs to some subset of the class of all distributions. And usually this concept class, the subset, has some common structure. So all the distributions in there have some common structure that the learning algorithm is supposed to exploit in order to make learning feasible. So if you wanted to relate this back to practice, think of again the example that I gave before with the faces. You might think of the concept class, for example, as being like distributions over images of faces. Then your learning algorithm should exploit that it's only ever going to see images of faces as input data. So you might think of a neural network that has some layers that are particularly built for it to learn some facial features or something, and maybe not learning images of landscapes. Okay, then also let me clarify that throughout the talk, I want the sample data that is the input to the problem to be purely classical. We as the group of co-authors and me, we think that especially in the distribution learning setting, this is the only thing that really makes sense. On the other hand, of course, the learning algorithm and the model output by it can be perfectly quantum. That's something that we allow and that we're also interested in studying. Then a crucial ingredient in the PAC framework is that we don't require the learning algorithm to be exactly correct. So it's fine if it outputs some model that is up to some epsilon, say in total variation distance, to the real distribution correct. And let me stress again that when I speak about a model, I might either mean a density model, so some way to evaluate probabilities of outcomes, or a generative model which is able to produce new examples. Lastly, to complete the picture, I will judge the complexity of this problem in terms of the runtime of the learning algorithm. let me note that you could also use sample complexity as a metric. So how many examples do you have to see before learning becomes possible? But this is not something that I focus here in the talk, because all our results are related to time complexity. And in the following, whenever I say hard, I actually mean that something takes super polynomial time in the number of bits. Okay, with this framework set up, let me just give a quick example so that we can all wrap our head around this framework. Consider the case of just learning product distributions over n-bit strings. So there's some unknown product distribution. You know it's product, so you know it has this form here, where it factorizes completely over the bits. And if you think about what the learning algorithm now has to do when it's given data, basically it just has to learn each coin independently because it's a product distribution. And so it will just estimate the bias of each coin from the samples. And it's sort of like, if you write it down, it's very clear that this can be done efficiently with few samples and also in polynomial time. So with this preliminary example out of the way, let us return to quantum circuit output distributions, because this is the concept class that we have looked at in our paper and are still trying to answer questions about. So just to be clear, the concept class contains distributions that are these output distributions of quantum circuits. And now the concept class sort of comes with two natural parameters. One is how deep we want the circuits to be. Surely when we make the circuits deeper, they become the output distributions come sort of more expressive. You can express a richer variety of distributions with them. And the other parameter is the gate set. So if we allow universal gates, then there's sort of no restriction. But if we choose a limited gate set that's not universal, we might restrict the class of distributions quite severely. And now coming back to the depth, if you think about like the two extremes that we could put in, if we only allow the circuits to be at the most depth 1, then the class of distributions that we can model with these circuit output distributions are still all product over 2 qubits, maybe if you use 2 qubit gates, but they're product. And that means that by the example that we just saw, learning must be easy. On the other hand, if we use a universal gate set and let the depth run to infinity, then this unitary here, we can approximate any unitary in that limit on the full unitary group over all n qubits. And that means that the concept class is also going to approximately contain all distributions. And in this case, learning can't be possible because there's no structure for the learning algorithm to exploit. The samples that it's seeing, it could just come from any distribution. So that's not possible. These are sort of the two extreme regimes, and that means that there's hopefully something interesting to uncover in between, where there's some sort of a scaling in the depths or something, and that's also what we find. So let me now show you our results. I will start with the dependence on the depth first. So how does the learnability of this concept class depend on the depth that we want the circuits to have? Our first theorem is the following. Distribution learning, general circuits, where I mean general means just circuits coming from a universal gate set of depth n to the omega O omega 1 is hard. That means, again, takes super polynomial time in both the generative and the density modeling sense. And this theorem is based on the existence of pseudo-random functions. And that's basically just because the proof crucially relies on embedding a pseudo-random function. So some cryptographic object into the output distributions. And this is an old idea that was already given back in '94 by Kearns and co-authors. And we've just taken it to the setting of quantum circuit output distributions here. So that's a nice result, but you might wonder, can we get the depth down? So what about the learnability of these output distributions at, say, much smaller depth? And I have an additional result here in this for a much smaller depth, namely like only super logarithmic depths, so much smaller than linear, say. And that's expressed in the following theorem. Distribution learning general circuits of depth d omega log n from statistical queries is hard, again, both in generative and density modeling sense. And now I've introduced this new concept here of a statistical query. This is something for the sake of the brevity of the talk, I can't really go into it that much, but basically a learner that's like the statistical query is sort of a restriction on the capability of the learning algorithm. But it's not a very severe restriction in the sense that most generic learners and any learning algorithm that I know from the variational quantum algorithms literature could be described as such a learning algorithm, learning from statistical queries, because these sorts of algorithms, they always rely on statistical averages over samples and not individual samples. So that's also nice. In this setting, we were able to get the depth down quite a bit. And that's sort of all we have. And whether we could get it down further is still open. And I'll return to this question later when wrapping up. Some more recent results are on the dependence of the gate set. So here we focused on the case of Clifford circuit output distributions, just because they are like, this is a natural gate set that has been considered a bunch in quantum information theory. And also another motivation for looking at Clifford circuits is this relation between what you can learn efficiently and what you can classically simulate efficiently. So we all know that Clifford circuit output distributions, you can perfectly sample from them in polynomial time. So the classical simulation side is very clear in this case. And that's where we sort of wanted to look at how does learning relate to it? Is it harder? Is it less? Or is it the same, maybe? So what's the alignment of the complexities here? And just to give you a few examples where these complexity actually are aligned, I've put some examples here. There are several papers on learning stabilizer states from data where it's been shown that this can be done efficiently, both in time and sample complexity. And also in the Aronson PAC learning framework for quantum states, it has been shown that stabilizer states can be learned efficiently. And that sort of gives the intuition that the complexity of these two tasks is often aligned when it comes to Clifford gates. I want to point out this particular example here where it's also been shown, or there are some preliminary results on learning Clifford circuits that also have some T gates. And also in their setting, they show that there's an exponential scaling in the number of T gates. So there's not really a hard transition there. So now what happens in our setting? In our distribution learning setting, we would just want to learn the output distribution of the Clifford circuit. We can show that this can be done efficiently, just as in the other cases, both in the generative sense and in the density sense. Basically, the algorithm boils down to recovering some affine subspace from data, and that is something that we can do efficiently by means of Gaussian elimination. But we make this sort of curious observation that when we go to the case where we just add a single T gate into the circuit, then in the density modeling sense of our problem, this immediately becomes hard. Essentially, we can embed into this problem the problem of learning parity with noise. And once you assume that this is hard, then we can show that in the density modeling sense, just a single T gate is enough to give you a transition from easy to hard. On the other hand, in the generative modeling sense, we don't really know yet. That's something that we'd like to figure out. So how this scales with the number of T gates that you put into the circuit. And that's in quite a dramatic contrast to simulation, where we know that just putting a few more T gates into a circuit, you can still classically simulate it perfectly well. Whereas in our setting, by the addition of the T gate, at least in the density case, learning becomes hard with a single T gate, where simulation sort of stays the same. Okay, so let me wrap up and then allow some time for questions, hopefully. So what is my wish list? We work in this, as I said before, we work in this very formal setting. And of course, we'd like to connect our results to practice even more than we hopefully already do. And one way that we could do this is we could try to lift our results from the worst case setting that we're currently operating in this PAC model, to an average case setting, where you don't require your learning algorithm to work always, but just on a large fraction of the instances, maybe. And that's sort of also a very common theme in complexity theory. It's very, fashionable at the moment. And another point on my wish list, I actually have a much longer wish list, but I just like to sample like what I think are the most interesting questions here. Another point is to crack this, to crack the problem of what happens at very shallow circuit depth, where you just like, can you learn the output distribution of a constant depth quantum circuit? And if so, like you want to give an algorithm that can do that. Or if it's not possible, then we might actually want to take our hardware results much further down in depth. So to just study this dependence on the depth more is something that I'd really like to do in the future. So that's it. Thank you very much for your attention. And
Thanks very much for an excellent talk. Are there any questions? Yeah.
So it seems if you have a constant depth circuit with only nearest neighbor gates, then kind of information could only propagate so far. What makes this different to kind of the product cases that previously talked about?
Well, in the everyone can still hear me, right? Yeah. It's true that on the level of the quantum state, you can use these light cone arguments to see that the state itself might have these limited correlations. However, on the level of the output distribution, you can actually get global correlations in depth too. So like this measurement sort of projects you into this very low, or like much lower dimensional space where you can generate correlations very quickly, even at constant depth. So it's not, at least we think that it's not very obvious how you can exploit this light cone style arguments in this case.
Any other questions? Yeah.
All of the results you stated, the hardness here was in the complexity for learning using just a classical. Was there any or was it for both if I have a classical and a quantum learner, or is it not?
Do you want to repeat the question? So I can also try to repeat it. So the question was that, like, whether these results actually apply to just a classical learning algorithm or also a quantum learning algorithm. And they actually apply to both. Yeah, that's the short answer.
I think we've got time for one more.
No, not really. I think like one of the main messages is that at least in this framework that we've set up, because we restrict the access of the algorithm to access the data purely classically, not like in a Q sample, superposition sample sort of fashion, we don't think that there's anything that the learner could actually do in the sense. On the other hand, I have to say that one of my co-authors, Ryan, has a paper from I think like 2 years ago or something where they embed a discrete logarithm problem in such a case, and they show that there are very, very contrived distributions where you can sort of construct in a quantum advantage, but not on this like general circuit sort of framework that we have set out here.
Yeah, I think I have time for one more question. Yeah.
Can you comment on the dependence on the accuracy parameter? Like how like you said that sometimes it's easy or like hard. So what's the dependence on the like I guess you use L1 more.
We use L1 norm.
So
Yeah, so the question was like, how does this depend on the total variation distance?
Right. This so our results apply. So since we have mostly hardness results, like I can tell you that you can this works for constant L1 norm distance even. So even with some constant L1 norm distance, it's still hard.
Okay, let's thank our speaker again. An excellent talk.